now let's look at how to run a nonlinear regression. So a linear regression is pretty straightforward, right? You just have a series of points, you draw a straight line. But a nonlinear regression, what it does is it allows for the possibility of curvature in your regression lines. So let's do this. I've already put some data in here, so you can go to Stat and Edit. You can see where I put the data then. And let's just go ahead and do a scatter plot. So to do a scatter plot, let's quit out of here. So you go second stat plot on. I'm going to turn it on. I'm going to do a scatter plot, my x and y. I put my x list and my y list here for my variables. And then I quit out of here and I'm going to go ahead and graph it. And you can see my data there in a simple scatter plot. So from there, what I'm doing is I'm going to quit there and I'm going to go to Stat, Edit, Stat, Calc. And before, what I did is I ran a linear regression here. But what I'm going to do is I'm going to put in a squared term. So the actual regression I'm going to run is going to be y is equal to, let's just go back and down and see it. We're going to hit quadratic regression right here. I'm still going to go L1, comma L2. Right, the way you want to do it is you want the first variable to be your x variable and your y variable, and then hit enter. And if you notice, this is your equation. Y is equal to ax squared plus bx plus c. And it's this addition of the squared term here that can give you some curvature. And here what I'm going to do is I'm going to go ahead and write down my answers here. A is equal to minus 0.108. B is equal to 6.256. And C is equal to 12.755. And I get R squared here. R squared here is going to be 0.86. So 86% of the variation in my model is explained by, in the data is explained by my regression model. So now what I'm going to do is I'm going to go ahead and go to y equals here, and I'm going to type this in. So then that's minus 0.108 times, I'm going to put x squared in parentheses, x squared, and then I'm going to go plus 6.256x plus 12.755. Now if I quit here and then I hit graph, you'll notice it plots a line, but notice the line that it plots. It doesn't plot a line, but a parabola, a quadratic equation. And what that allows for is the curvature in the graph. Now, the key is not just how well it fits the data, but let's compare it how well it fits the data compared to how well it did if we did a line. So let's go ahead, let's leave that line there for a minute. Let's quit here and let's clear here. And now let's run a linear regression and let's compare the two. So here you go down here, you go to Lin Reg and L1, comma L2. And let me go ahead and write down that information there. There you have y is equal to ax plus b, and a here is equal to 1.295, and b is equal to 55.755. R squared now is only 0.60, so clearly we explain a lot less than we did in the last regression. So I'm going to turn this off. The way you can turn this off is put your cursor on the equal part there and just put enter, and see how it's no longer highlighted. I'm going to highlight this one, and I'm going to go 1.295x plus 55.755, and then I'm going to graph that, and you can see how the line goes through. Now you can compare it. You can say, well, how well does this explain the data versus, let's go back to y equals. Now let's turn this one on, this line on, and let's turn this line off. turn it back on. The way you do is you put your cursor on the equal sign and push enter and see how it's no longer highlighted. So I'm going to hit zoom 9 again. And there's actually statistical tests that you can tell about whether or not one does better than the other. But clearly on this simple data set here, we can see that the quadratic equation does it much better than the linear equation. And that's how you do a nonlinear or quadratic equation.